Okay, welcome everyone to our webinar titled New Frontiers in Air Quality Research, Observational Improvements from both the Surface and Outer Space. My name is Ren Smith. I'm a member of the AGU Atmospheric Sciences Early Career Committee. I'm going to open with just a few words about our committee, and then I'm going to introduce our moderator for this session to go ahead and kick things off. So the AGU Early Career Committee provides resources for and creates and promotes professional activities for early career scientists. For this webinar series, we plan to have at least 2 more of these, but probably 3 more of these early career webinars in 2024. So we invite you all to join us for those. And also, if you want a chance to present at one of these, we're perpetually accepting abstracts using the link that I have here, which one of us will paste into the chat for you. In 2023, our committee held webinars on professional development, DEI, and tips for navigating the fall meeting for early career scientists. Right now, there's nothing concrete scheduled for these topics in 2024, but you can keep up by following the Atmospheric Science section's newsletters or our committee's Twitter account, which is listed here as well. And you're also free to email our committee at any time with questions using the email address we have listed here on the slide as well. I want to let you all know that this meeting is being recorded. It's going to be posted on the AGU YouTube channel as well as on our committee's website. And lastly, I'll just mention that we have a feedback form for today's webinar. If you wouldn't mind taking a couple minutes to fill that out afterward, we would certainly appreciate that. We're always trying to improve and make these as best we can, or make these go as smoothly as we can. So we'll post that link in the chat also. Okay, so without further ado, allow me to introduce our moderator for today's session, Amena Ijaz. Amena is a postdoctoral researcher at the Laboratory for Environmental Chemistry of the Aix-Marseille University in France, studying source apportionment of submicron aerosol pollution during the winters in Fairbanks, Alaska, using online mass spectrometric techniques. She received her PhD in 2021 from Michigan Technological University, where she was a Fulbright scholar, working on molecular level characterization of wildfire smoke in the Pacific Northwest. So thank you all for joining us today again, and we'll go ahead and turn it over to Amena to moderate. Thanks.
Thank you so much, Ren. I'm very pleased to be here and for this opportunity, and I'd like to welcome everyone to today's seminars on air quality research. We have 2 speakers, Dr. Zhaocheng Zheng and Dr. Taikyu Zhu. The first speaker would be Dr. Zhaocheng Zheng. I'd give a brief introduction for him, and then, but the one thing that I would like to mention is that as he is presenting, it's okay for you to submit your questions in the chat box, and we'll come to them for a couple of minutes right after his talk. And then we will hopefully have a much longer conversation on both the topics at the end. So Dr. Zheng is an assistant professor at Peking University in China. His research interests include radiative transfer and inverse modeling in atmospheric remote sensing. He is currently leading a research group at Peking University to measure global greenhouse gases and air pollutants, and he is trying to understand their evolution using China's Fungyun series of satellites. He will speak about tracking carbon monoxide, ammonia, and VOCs over Asia from the world's first geostationary hyperspectral infrared sounders. So that sounds very exciting. And with that, I'll hand it over to Dr. Zheng.
Thank you, Amna, for the very nice introduction. Let me share my screen. Can you hear me okay?
Yes.
Thank you. Good morning and good evening, everyone. I'm very glad to be here to share with you some of our recent work on observing carbon monoxide, ammonia, and VOCs over Asia from the world's first geostationary hyperspectral infrared sounder. That is the GERS instrument on board Fungyun 4B satellite as shown in this right-hand side image. Before I start, I would like to thank my collaborators from the National Satellite Meteorological Center and from ULB in Belgium, as well as my students and postdocs at Peking University, all listed here. Next slide. So for those of you who are not familiar with China's Fungyun meteorological satellite, so the name Feng stands for wind and Yun stands for clouds. So as its name suggests, The satellite's primary goal is to improve the numerical weather prediction. But beyond that, in recent years, many new satellites have been launched to monitor atmospheric radiation, air pollutant, and greenhouse gases. So the right-hand side image shows the in operation satellites. There are 9 currently in the sky, and I just want to highlight 2. Before that, I want to mention that the odd number series, for example, FY3 here, is polar orbiting satellite. And for the even number, for example, FY2 and FY4 are geostationary satellites. And also we have the alphabet table. For example, B stands for the second satellite in the Phone 4 geostationary series. And I want to highlight 2 satellites here. The first one is this Phone 3E, which is the actually the first civil dome-dust polar orbit satellite with overpass time at 5:30 a.m. and p.m. And the second one I want to highlight is this geostationary satellite Phone 4B, which is the focus of my study. And all the spectra and higher level data are actually publicly available through the this National Satellite Meteorological Center's website. So some brief introduction of this GERS instrument, and it scans the study area in a steps demo. And each field of view, it collects 16 times 8 interferograms by the detector as shown in the middle. And for the full region, there are 27 field of regards and 12 scans. You can think of it as 12 rows and 27 columns. So the whole observation takes 2 hours. So we have 12 maps in a day, cover day and night, and the footprint size at nadir is about 12 by 12 kilometers. So this shows a very typical spectra in thermal infrared in brightness temperature as a function of wave number. The spectral resolution is very high, 0.625 wave number. And the red line here indicates the spectra coverage of GERS instruments. So using this spectra for the purpose of numerical weather prediction, people can use CO2 and water vapor bands to retrieve the profiles of temperature and humidity. And for us, we can take advantage of the absorption features of many trace gases, including air pollutants and greenhouse gases, to do the retrieval of the profiles of these compounds. So in this study, I will focus on 3 trace gases, carbon monoxide, ammonia, and formic acid. So some very brief introduction of these gases. Carbon monoxide is very familiar to all of us, I believe, and it mainly comes from incomplete combustion. And because of its relatively long lifetime, it serves as an effective chaser for air pollutant and carbon emissions. For ammonia, its primary source is from agricultural activities. It has many negative environmental impacts on water bodies, ecosystem, and human health. Formic acid is one of the most abundant volatile organic compounds and also important source of atmospheric acidity. The direct emission come from vegetation and biomass burning and fossil fuel combustions. Also, a lot of them come from secondary formation. And so it's very, very important to monitor these trace gases if we want to really understand the evolution of the atmosphere or to predict the air quality of the atmosphere. So I will focus on these 3 compounds, and the spectral range is listed here. So the first step is to construct a retrieval algorithm. So we do it using the quite conventional optimal estimation. So the basic idea is to match the spectra. So as I give example here for carbon monoxide over a small window, and the red line here shows the GERS observation, and the blue one shows our simulation from radiation transfer. So the goal is to match them until the fitting ratio close to the spectral noise, then we think it gets to the best fit. And then we can get the state vector, which is the retrieval result. And in practice, we usually try to minimize this cost function by minimizing the difference between the observation and our radiated transfer and the state vector and the a priori. I'm not going into too deep into this equation, but a lot of details are in this paper publishing AMD and in some of our my backup slides. And I'm happy to take question if you have on this retrieval algorithm. So in the following slide, I will just focus on the monitoring the fire emission from Southeast Asia. And every year from January to April, there are very intense fire emissions in Southeast Asia, mainly from the slash and burn agricultural activities. Also, when loggers use fire to clear roads and lands, together with cool and dry weather, all leads to very strong fire emissions. And as example, I show these maps of three compounds on April 11th, 2023. Is in the local noontime. And if you look at the CO column retrievals, you see a large enhancement around this region. And also you can see the transport towards the ocean. Similar pattern can be seen from for the formic acid and ammonia. But you see that formic acid and ammonia has relatively shorter transport range, probably because of their shorter lifetime. So now let's check the diurnal cycle. So I make this video using many maps of CO columns for every 2 hours and using all the data in April 2023. And you can see the fire emissions of CO transported towards the South China Sea and eventually go to the Pacific. And the diurnal cycle, the day and night cycle, to check that, I do this 2 hour average over the land region. And you see this is quite a typical diurnal cycle of fire emissions with high value in the daytime and low in the nighttime, probably caused by the change in temperature, humidity, and the agricultural activities. Now let's take a look at formic acid. Similarly, we see a very strong enhancement keep going out of these burning regions and transport eastwards. And compared to CO, we see a much stronger diurnal cycle. Probably because first of all, the lifetime is shorter than CO. And also most of the formic acid enhancement comes from photochemical production, which is much more intense during the daytime. And this enhancement can be seen in this 2 hour average over the land region as well. However, we should be very careful when we try to compare the measurement in the daytime and nighttime because the vertical sensitivity is very different when we use the observation from thermal infrared. And this vertical sensitivity is actually primarily driven by the thermal contrast, which is defined by the temperature difference between the surface and the lower atmosphere. When difference is large, we see we can get a lot of sensitivity of the lower atmosphere. But however, when the temperature difference is very small, like in the nighttime, we lost detectivity of the lower atmosphere. And we usually use degree of freedom for signal to represent the information that's available from the spectra, and which can be, and this degree of freedom for signal can be calculated from averaging kernel. So I make this averaging kernel diurnal vector here, and its physical meaning is so for the x-axis, it represents the degree of freedom, like how much information actually available vertically. So the y-axis is the pressure. So in the daytime, see this light yellow and light green, it's very high, and it means we have a lot of signal from the lower atmosphere for CO. However, in the nighttime, see this dark blue and dark red here. Most of the information actually from free troposphere. So we need to be very careful, and we need to take this kernel information into account when we compare the daytime measurement and nighttime measurement. Similarly for formic acid. Since it's very difficult to make direct measurement from ground, and actually there are very limited ground-based data for the validation. Also, it's very difficult to make nighttime measurement. So what we do is do the cross comparison with YADI, low Earth orbit instrument, and the comparison looks very good. And we also have done some collocation comparison in data pairs, and similar result can be seen for formic acid and ammonia. This indicates that observation from a geostationary satellite have comparable sensitivity to lower Earth orbit. So in conclusions, GERS is the world's first geostationary hyperspectral infrared sounder, and we developed the algorithm to retrieve CO, ammonia, and formic acid. And we show that it can successfully track the day-night cycle of Wi-Fi emission in South Asia, and the detectivity is determined by the thermal contrast primarily. And we believe our observations will offer important information to check to understand the production, evolution, loss process of these compounds. And lastly, we have two related publications in AMT for CO and ammonia, and the data, the spectra and the retrieval data also are publicly available. And thank you, and I will be happy to take any questions or comments.
Thank you, Dr. Zheng. That was a very interesting talk, and there was lots to learn for at least me, because this is way outside of my scope. So while I see that do we have any questions now? Okay, so audience, please feel free to leave your questions here, or you can even raise your hands. But while we get any questions, I'll get the conversation going. So I was wondering, you're looking at carbon monoxide, ammonia, and VOCs, but this is remote sensing, right? When you're looking at things from way above, are there any interfering species? How do you account for that?
There are many interference gases. Let me show you an example here. So look at this with small window. Target gases is carbon monoxide, but we have interference gases like water vapor, CO2, ozone, and nitric oxide. But the absorption feature of them are different from each other. So we take advantage of this, and we can retrieve separately of different gases. But of course, this is a spectral window primary for very strong CO absorptions. So we can have more trust in CO results instead of other results. So these interference gases are there, and we fit them as well, but we don't use them for analysis.
Okay, and they don't contribute to the uncertainty, but they do, but you subtract that uncertainty out.
That's right.
Okay. So, and this is again a very basic question. From what I understand, you do see differences in the accuracy, if that's the right word, between day and night. But when we're looking at the atmosphere from way up above, you're also looking, there's clouds, there's other things. But does the sensitivity actually change from the top of the atmosphere to the surface? And because I'd assume that, considering the species that you're looking at, whatever is close to the surface is the most relevant to us.
That's right. That's right. For wildfires, I think the plume can reach like 1 or 2 kilometers, but still most of them are located in the lower atmosphere. And for a question regarding clouds, we actually have to filter out all clouds and focus on clear pixels where we can see the lens. And in this way, most of the sensitivity can get to the surface layer where most of the emission are coming from.
Okay, I get it. Thank you. So now we have a question from the audience. Alyssa asks, what are planned future uses of this sensor other than for wildfire applications?
Thank you for your question. So we have, over this region, there are many mega cities, and this mega city emit emission as well. And Well, let me show this video again. You see, for CO, it's not just from this Wi-Fi emission. It's from, for example, the northern China plain, where many big cities are located. But you can see the emission enhancement of CO. But because the Wi-Fi is so strong, I need to adjust the color bar in order for us to really to study the enhancement of the urban region. But for other seasons, when there are no wildfires happening, most of the high CO emission are actually coming from urban areas. And for ammonia, let me show you this map. You see, besides the emission from Wi-Fi, we also have the high value from agriculture area in northern parts of India and in North China as well. So there can be many applications besides Wi-Fi emissions. I hope that answers your question.
Yes, at least for me, yes. But thank you so much. So we do have several more questions, but I believe it's time to move on to the next speaker. So thank you, Dr. Zhang, and we'll come back to the other questions after Dr. Ju's talk. So, okay, I will introduce Dr. Ju, who is an assistant professor at the Department of Earth and Environmental Sciences at Korea University. He did his postdoctoral research at Yale University and did his PhD at Georgia Tech. So far in his career, he has been investigating the impact of biomass burning on air quality, climate change, and human health through lab, chamber, and ambient air field experiments using mass spectrometric techniques. So, oh yes, and he will be presenting on aged and obscured wildfire smoke associated with downwind health risks during the Canadian wildfires in 2023, particularly in New York City. So the floor is yours, Dr. Ju.
If I'm muted.
Yes.
Now it's fine,
You're good
right?
now. Yes.
All right, thank you very much for the introduction. So today my presentation will be about the aerosol composition analysis during May to June 2023 Canadian wildfire influence on the New York City and looking into its implications for the public health. So before starting the presentation, I would like to first acknowledge NSF and NYSERDA for the support on this work, and NYSDC for help in the site operation. So I just recently moved to Korea University, and this work is mainly from during my postdoc years at Yale. So as some of you may are aware of now, Canadian wildfire was a serious air quality challenge that many parts of the United States encountered last summer. And this is a photo how it was severe in New York City during that period. And in New York City, this was the record peak of the PM 2.5 level, which was the worst air quality on the record. So PM 2.5 during this period reached up to around 460 microgram per cubic meter and daily average of around 200. So this is much higher than the regulation level of which is the 35 microgram per cubic meter for the 24-hour standard in the United States. But just one thing to note, now following the new WHO's guideline, EPA have lowered the annual standard from 12 to 9 microgram per cubic meter. So we set up a long-term monitoring station in Queens College in New York City, and since 2022 summer. And this was as a part of the nationwide project called the Ascent. And luckily, we were able to capture multiple Canadian wildfire influences in last summer. As you can see from the right figure, where the originate of each fire during the experimental period is shown. So we used aerosol chemical speciation monitor for the non-refractory species measurements, accelerometer for the black carbon and brown carbon measurements, and exact for the trace metal measurements. So all the supporting pollutant measurements, including PM 2.5 mass concentration, NOx, SO2, etc., are measured by the New York State Department of Environmental Conservation. So during the summer, dramatic enhancements of PM 2.5 was observed, especially in June 6th to June 9th. And it was predominated by the organics, followed by black carbon, which is colored, it's in purple in the pie chart and the time series, and the nitrate, which is colored in the blue. So although the overall trace metal measurements, which is shown in here, was relatively low, we observed strong enhancements of the potassium, which is a well-known biomass burning tracer. So leveraging the real-time measurements of this potassium, we identified 5 potential fire events that were accompanied by some noticeable level of the organic and the total PM 2.5 enhancements throughout the sampling period. So based on these measurements, we further performed back trajectory analysis during the experimental period. And during the wildfire influences in the figures here are the representative case of the trajectory affected by Western Canadian and then Quebec wildfire smoke that is transported toward New York City. And from the trajectory analysis, lower PM concentration from the West Canadian wildfire smoke influence was not only owing to the long-range transport aging, but it looks like it also capturing the smoke plume rather than the air plume here is directly transported from the point sources, which is the case from the Quebec wildfire transport events. So considering both trace metal measurements and the back trajectory analysis, we identified the Western Canadian wildfire smoke was more frequently transported over the New York City in May, and strong impact of the Quebec wildfires during June, and with an effect of the Quebec wildfire plume affecting again in June 10 to 13 after being aged over the Atlantic Ocean, as you can see from the back trajectory analysis that is shown in this figure. So as the organics are the main component during the wildfire smoke intrusion period, we further performed source apportionment analysis using the positive matrix factorization onto the organic aerosol dataset and identified 6 different factors. So other than the 2 biomass burning related factors, which are the BBOA colored in brown and aged BBOA factor colored in blue, so 4 factors, which are the LOOA, MOA, and COA, HOA, are the same to the previous study that was conducted in summer 2022 by Hasmitchell et al., which is published recently in the ESNT. And during this study period, we didn't see strong influence from the biomass burning smokes. So while the main wildfire event in June was substantially affected by the primary biomass burning factor, the other periods are dominated by oxygenated organic aerosol, which is kind of widely considered as the surrogate of the SOA, secondary organic aerosol, in the ambient measurements that you can obviously see from the pie charts in the upper part of the figure. So this is especially well shown in the oxidation state, which is in the dark green, and the O2C ratio estimated, which is colored in light green markers here. So here, it's the West Canada wildfire shows higher oxidation level compared to the Quebec wildfire smoke influence periods, which are less, and they are kind of less oxidized. And when we look into the more F60 signal, which is the levoglucosan-related fragment and the biomass burning tracer of the organic aerosol, this shows the much stronger enhancements from the Quebec wildfire intrusion periods compared to the wildfire that is originated from the Western Canada. And the aged Eastern Canadian wildfire on the very right here shows the slightly more enhanced F60 compared to the West Canadian wildfire or the early June Quebec wildfire, which is in the middle. And then compared to the major wildfire intrusion from the Quebec wildfire, it's slightly more oxidized. So the results here and the previous slide show that it is kind of difficult to identify the actual source of the organic aerosol by just the PMF analysis on the organic aerosol alone. Using the metal data in tandem with the ACSM dataset allowed us more robust source apportionment of the biomass burning impacts on the PM 2.5. And we further performed analysis on the public health effects owing to the wildfire influences. So the left figure here shows the analysis on the asthma-related emergency room or the department visit cases response to the aerosol compositions. So based on the analysis of the previous slide, we classified the smoke OA as the sum of the BBOA, HBBOA, and the two types of the oxygenated organic aerosols. And figure here shows the increase in the daily emergency department visit cases over most of the age groups, and it was associated well with the elevated organic aerosol level. And we further performed this analysis with the potassium, which was well correlated with the smoke-related OA, regardless of the considering the major wildfire events, which is the Quebec June 6 to 9 wildfire events, and shown in the right figure here that you can see the comparison between the brown markers versus the gray markers here. So based on these results, coming back to the epidemiological analysis on the left, the potassium can also serve as a good marker, well associated with the daily EDV case changes, indicating that these species can serve as an effective confirmational indicator in the epidemiological analysis. And we note that there could be some other sources contributing to the public health effects, but the vast majority of the smoke-related OA is from the biomass burning during this period. So we believe this is mainly affected by the biomass burning during this experimental periods. And last but not least, we tried to estimate organic aerosol composition-dependent potential oxidative stress to evaluate the health effects. So we adopted results from the previous studies that evaluated the correspondence between the organic aerosol PMF factor and the oxidative potential or the reactive oxygen species analysis, and used those values as the coefficients and adopted into our organic aerosol PMF factors that we obtained from this study. And we performed the Monte Carlo analysis and reported as in the enhancements. So in this way, we designed this analysis to be as inclusive as of the prior work as possible, since these previous studies that we adopted each of them used a different oxidative stress enhancement methods and also contains different types of the source factors. So the box whisker here shows the most severe oxidative stress would have come from the major wildfire smoke event, which is the Quebec June 6-9 wildfire transports. But when it's normalized by the organic aerosol mass enhancements, the Western Canadian wildfire smoke transport shows the higher potential oxidative stress enhancements. So in other words, more aged smoke plume with the limited molecular tracer signature presented greater potential oxidative stress enhancements per unit mass on the average. So to conclude and summarize, this long distance wildfire plumes represent a substantial source of PM under New York City under the changing climate, and which is kind of predicted to increase in the wildfire frequency and the intensity in the future. And identifying these PM sources exclusively through the organic aerosol PMF analysis can be somewhat ambiguous due to some oxidations and followed by some of the loss of the key markers of the primary tracers. So real-time measurements of the potassium and other trace metals can improve identifying this transported wildfire smoke and then some of the low-intensity events. And the epidemiological analysis that we tried here using this speciated PM shows the increased relative risk of the acute asthma-related health effects that can be associated with the smoke-related OA or the potassiums. And the potential oxidative stress estimation demonstrates that extended aging processes have some potential to possess a health risk. So this is all for my presentation, and thank you for attention, and I'm happy to take any questions.
Thank you, Dr. Zhu. You were exactly on time. This was a very interesting presentation. So I'll see if we have any questions from the audience. Okay, so not yet, but okay. So I was thinking that you saw a lot of difference in the O by C and even the oxidative potential of the wildfires that were happening in Quebec and then those that were happening in West Canada.
Mm-hmm.
But do you think it could be distance, it could be a factor, but do you think meteorology between, I believe, May and July, do you think meteorology or how much cloud cover was there, how much solar radiation was coming, temperature, were those factors playing at all in that?
Yeah, so actually we also did some calculations based if any like wait, do you mean the transport affected or like our estimations been affected or?
The actual measurements, the differences that you're seeing, why do you think you're looking at, why is there such a huge difference between them?
Oh, yes. So actually, we also tried to look into some temperature dependency on this like our estimations here. But the thing is that so the previous study that we showed earlier, that in that case we saw some temperature dependency on the OA or the MOA signals. But in this case, we weren't able to see that difference. So I think just based on the chemical composition part, there could be somewhat limited effect coming from those temperature. And since this was a little bit earlier than the like actual summer began, also that could be one of the reason why we've been seeing less relationship with the temperature dependency there. And then it was mostly affected by like that period is kind of focused on the effects coming from the biomass burning and because of that reasons too.
Okay. So now you just mentioned, and I believe it was on the slides too, that when you do your PMF, your factorization source apportionment, you have a more oxygenated organic aerosol factor and then also an aged factor. And generally, the more oxygenated is considered the aged factor. So on what basis do you have those two factors? How are you separating them?
Oh, you mean like more versus less oxidized?
So more and less is the conventional differentiations that people make, right? But you also have an aged organic aerosol. So how do you differentiate between the more oxygenated organic aerosol and the aged one? Because I always thought that maybe that's the same thing.
Yeah, so I think so based on how we separate that oxygen organic aerosols is that we use if we use AMS, it's gonna be looking into directly O2C ratio comparisons, but in the ACSM, we don't have a way to measure O2C ratio since so we kind of use somewhat the ratios between the F44 to F43 ratio comparison. And that way we can kind of get some sense of which factor could be which more oxidized than the others. And that way we separated out the two OAs there, but there are definitely some uncertainties reported in the separation of the less oxidized versus the more oxidized. And maybe I can just add also one thing, part of the aged biomass burning factor.
Yeah.
That one has been kind of separated out entirely, just dominating during the June. Maybe it might be a little bit easier by sharing the screen again. So during this period, like at the end of the later part of the Quebec wildfire smoke event and this another returning wildfire plume, we kind of saw different aged factor appearing a lot. I mean, taking a lot of the fraction of the total organic aerosols, and that way, and we kind of also run the high split analysis, a back trajectory analysis during this period, and then that's where we kind of found out the June 5, 6 to 9 wildfire plume was transporting over Atlantic Ocean and age and then coming back. So we kind of found out that it's definitely affected by biomass burning plumes, but it's being more aged. And then this time series, it's been separating out from the PMF analysis. And then if we look into some tracer, more details in the O2, like the O2C ratio, which we estimated based on the F44 signals from the ACSM, was showing that a little bit higher, slightly higher than the period during the major wildfire plume transect period, with a little bit slightly higher F60 values compared to other like the more aged wildfire periods. So that's how kind of we also separate out this more aged biomass burning parts.
Yeah. Okay, I get it. Thank you so much. So we do have a question from the audience. Ren asks, he says, nice presentation. And then he asks, maybe I missed this, but what are the time scale differences between the fresh nearby fire influence and the more aged fire influence from I think this is what we were just touching upon, but I'll
Yes.
complete the question. Fire influence from the different events based on the trajectories, and also just out of curiosity, what analysis winds did you use for the trajectories?
Sorry, I don't kind of understand about what wind means here, but I was wondering if the trajectory analysis that I just showed you might kind of answer that questions, since we can see kind of that plumes really traveling all the way outside the Atlantic
Yeah.
Ocean and turning back. I hope
So they
that
took
answers.
they took a
Yes.
swirl and a loop, and
Yes.
because they traveled more is why they
Yes.
ended up being. I hope that answers your questions, your question, Ren. If not, you can even turn on your mic and raise your hand. So along the same lines, in New York this is over New York, so which is a very urban. So you also have emissions, local emissions, right? Not
Yes,
just the
right.
wildfires, and you might have SO2, and you also have NOx and whatnot coming from traffic. So how did you see a local how much was the local influence that you were able to see in your PMF? I saw, because there was a cooking factor. I just saw it, right? So there must be a there must be a local influence too, and how it didn't seem to be too much, but could you comment on that?
So yes, so sure. So probably some of the COA, like cooking, or the HOA, the hydrocarbon-like OA factors, those could be more kind of local, relatively,
Yeah.
compared to the more oxygenated organic aerosols or some of the biomass burning in cases here. And then those generally took around, I guess, around sometimes 20%-ish, but mostly 20% to 10%. But during the main biomass burning period, because that plume was really having really high concentration of the PM, so I believe the contribution from the local part would be a little bit limited during that period.
I see. So audience, please don't feel shy to write any questions, and I'll keep going on, but it would be nice to hear from you as well. So my last question, Dr. Ju, here would be that I know that your presentation right now is focused on more of the health influence, but based on how much you're looking at aged OA, and then this is biomass burning, especially from wildfires. So you'd expect to see tar balls, you would expect to even form brown carbon, loads of it. So did you by any chance do any side fund projects where you were looking at also the climate impacts?
Oh, yes. So maybe we kind of look also into some brown carbon measurements, but mostly we just use as an indicator or of the biomass burning or our own sanity check with the comparison with potassium data or the BBOA factors that we have. But probably there might be one thing interesting that we can extend it further. But since the climate impact might be a little bit more related to a little bit more long-term measurements, so I believe our other, like the colleagues in the group, will kind of work on the long-term monitoring or the measurements at the New York City. Maybe in that paper, we can also add some insights about looking into the climate impacts there additionally.
That would be a fun thing to do. It looks like this was an amazing data set, definitely. So thank you, Dr. Ju. And we do have a question from the audience. They ask, they say it's Alyssa. She says, this is a simple question that may be outside your area of expertise, but anyway, do different types of wildfire fuel, for example, different types of trees, grasses versus trees, impact the composition of the smoke of the wildfire? And then they ask, could this be an avenue for determining where wildfire smoke is coming from if there are multiple wildfires burning in different locations at different times?
Yeah, so this might be a little bit outside of today's presentations, but if you see some of other more speciated analysis, there are definitely difference in some of the emissions depending on the fuel types. So if we look into more general families of each kind of types of the organic vapors, then you might able to separate out some of this sources. But another thing is that because of aging from the biomass burning, there could be some mixed in the sources there. So there could be also difference by the fuel types, like the moisture level of the fuels, and how long it has been transported. So there are a lot of missing parts there.
Yeah, just to add to it, I believe if in AMS and ACSM analysis, because everything just turns into a soup, you don't really get to see so much separation. But if for molecular analysis, there have been studies where they can actually separate using PMF, the same method that you've used between even hardware sources or software sources. So that happens, but from more, I think, molecular spectrometric approaches. So then we also have another question. And they're asking, thank you for the presentation. Why are the aged plumes, why do they present more health risk, and what compositions may play a major role?
Oh, yes. So there are also some of the recent work that I was also co-authored that maybe the oxygenated organic aerosol or the highly aged and the more having high O2C ratios might be somewhat associated with the cellular responses based the reactive oxygen species measurements. So that could have some effects onto the have some more implications why this aged transported the plumes can have some more say detrimental effect on the health. But also one thing is that of course that biomass burning would emit a lot of very toxic materials or the vapors. But in terms of this maybe oxidative stress part might be somewhat related to this oxidation level of the organic aerosols. But I think we are people are in the health field, or the people who work on this related topics are keep working on looking into what is exactly the reason why this all this some of the aged organic aerosols are showing strong correlations or the relevance with these ROS measurements.
Yeah.
Mhm.
Okay. Thank you, Dr. Ju. We've had an amazing discussion on your presentation, and it was again extremely informative, very fun. So I remember we had two questions for Dr. Zhang, and I see that he has answered them in the chat. But if you're okay, it would be still nice to have a discussion on them, because this is eventually recorded, and it would be nice for the people who might see it later. So one of the questions that we had for you was, great talk. Have you found signals of dust, particularly in the SWIR to thermal channels? How do you filter them out? Oh, but you're muted.
Okay, good. Thank you for the question. And we actually haven't looked into the dust signal by ourselves. Instead, we rely on a observation from an imager called Mercy on board the same satellite that can have a better detect of the clouds and dust things. And we rely on this observation to filter out the dust and clouds, to make sure that we only use the very clear pixels for our retrieval.
Mm-hmm.
But surely the dark signal should also exist in the hyperspectral observation we're using. But we haven't really taken time to look into that yet.
Thank you. And then Stuart asks, what is the spatial resolution of the ammonia sensor?
So the spatial resolution is 12 kilometers in nadir, and off nadir, it can become very large, much larger than 12. And I believe it's somewhere between 20 and 30 kilometers.
I see. Oh, okay. Thank you. So, Dr. Zhang, I have a question for you, and this is coming from Dr. Ju's presentation, but it is for you, because when you're looking at VOCs, I'm assuming not just formic acid, but others too. You can, hypothetically speaking, and you also have carbon monoxide, you have ammonia, and so different species, and you are measuring concentrations or estimating them. I'm very bad at this remote sensing things, but that's what you're doing, and you're doing it over time with low temporal resolution or high temporal resolution, but definitely over time. So can you use that data from satellites for source apportionment the way Dr. Ju does it for his ACSM data? Can that be done? If you have several variables, not just three.
Yeah. So VOCs, I only show example of formic acid, but we can detect some other signal from other VOCs like PAN and say C2H4, and some of these compounds can be easily detected if the instrument is sensitive enough, and we do see the signal. But of course, I wish our observation from sky can be as accurate as what you have been doing with ground-based
So it's not.
observation, but it's very challenging. I have to tell
Yes.
it's very challenging because what we are measuring is the total count, which is the
Yeah.
integrated number of molecules integrated from the surface to the top of atmosphere, and we have different sensitivity. Sometimes we have higher sensitivity to the surface, sometimes in the free troposphere. So we have to rely on transport modeling to do the assimilation in order to back out the emissions. And if we want to look at into the details, especially the spatial and temporal change of the emissions.
And that's an interesting point, because you say that it's all those satellites, I would say, are more, the data from them is more accessible, right? But you're saying that it's not as accurate. But if it was to be that accurate, or if it was to if it were to improve in the future, it could fill that gap that low income countries, like I'm from Pakistan, we cannot have fancy instruments like ACSM or the EMS here to actually do real-time online studies.
Right.
So if we could use satellites for that purpose, that would be really nice. But I believe that they need more improvement as compared to the observations to be used for that purpose.
That's a good point. And for example, for some events, that is say anomaly emission that is so strong, then we can surely detect it from space, and even with a relatively coarse resolution or relatively bad accuracy, we can still see the enhancement very clearly.
Yeah.
So over these large events, there's no problem from current capability of the satellites.
Yeah. And I do say, I believe there was a slide where you did discuss that you were comparing with some estimation or simulation with some observations, correct? So where exactly were those observations coming from? Were they ground-based observations or were they satellite observations? There was a slide.
There are still satellite observations from the low
All
orbit.
right.
Yeah, because they have been doing that for more than a decade, and they have conduct some validation with some ground-based observation elsewhere outside of Asia. So we believe that because it's a independent satellite, independent algorithm, so we think the comparison should tell us something about the accuracy of our products.
So Dr. Ju, when you're looking at your ground-based measurements, sorry, I just jumped from one person to the next.
That's okay.
But you are also doing some, your trajectories are coming from satellite observations, correct?
Well, I think that's kind of based on the models like provided by NOAA. I think maybe yes, but I need to double check exact source.
It's very, I find it's extremely nice that we have one person you're looking at the same thing technically, but one of you is all ground-based observations and the other one is all satellite observations, and it's really nice and essential to bridge that gap, correct? So I'm trying to know because we're very close to ending, right? So I'm trying to stimulate you into speaking. How do you bridge that gap between modeling, and if you would like to comment on it a bit and just till we end, would you like to comment at all, both of you? How do you bridge your modeling studies with ground-based and observations, and how do you bridge your ground-based observations with modeling studies, because they're highly dependent on one another and sometimes often competing too?
Yeah, so for maybe exactly that's kind of the why we are setting up the Accent network over all around the US. As same as, I mean, it's kind of like benchmarking, like following how the actors did in the Europe. And then that's setting up in the US, where we're trying to set up all this real-time measurements around each part of the United States so that we can gather all this data and then maybe kind of contribute also to some of the improvements in the input data on the model. So I think there has been already good efforts to trying to have some those bridges between the modeling work and the observations, so that we can improve like the both ways, like it can benefit both modelings and then probably improving also the measurements that other people or the modeling people can also be interested in. So I think there's been a lot of like things
Yeah.
or communications going on between the two communities to have more better science, or also get some good insights, or provide some good information for better policy, like the establishment of the better policies too.
Very
Mhm.
important for mutual benefit.
Yeah.
Yes.
Mhm.
Dr. Zhang, would you like to add some comments? We do also have a question for you, by the way. It just
Okay.
came in.
Yeah, and this is what we call assimilation. Basically, trying to for example, adjust the model simulations by our satellite observation. People have doing that for many years. But previously, before this geostationary satellite, people rely on observation from LEO satellite. Basically, you have two at the nighttime and daytime, and to drive this or to assimilate into the model simulations. But now we have geostationary satellite, which can make measurement every 2 hours, or can even every 1 hours. We have more measurement, and therefore, if we can assimilate this observation into model, we will have a much accurate, at least for the diurnal cycles of these emissions.
For sure. Okay, thank you so much. And then we have one last question for you, Dr. Zhang, and then I'll hand it over to the organizers. Kamran asks how surface albedo affects the retrieval of these different species, carbon monoxide, ammonia, etc.
Thank you for your question. So albedo, we usually in thermal infrared, we usually more care about the emissivity. That is the how much energy is for example, is emitted from the surface at certain temperature, and that's a factor we have to multiply to calculate the actual radiance coming from the surface from the atmosphere. And for this emissivity, for example, surface emissivity, it has a large impact. Especially over regions, we do not have very accurate estimate of emissivity. Currently, in our method, we don't estimate that. We adopt a quite mature product from Modis. So Modis team has this global emissivity database. We just use there for our retrieval. We believe they should be accurate enough for most of the region.
Okay. Okay, thank you so much, Dr. Zhang and Dr. Zhu, for very engaging talks. They were very nice, lots to learn. We do have a feedback form in the chat box. And with that, I would like to thank both of you, but I will hand it over to the organizers if they have any last minute comments or something. And thank you so much. Thank you to the audience as well for engaging.
Yeah, absolutely. That's the only thing I have is thank you very much thank you very much to our moderator. Thank you very much to our speakers. This is a really excellent session. And thanks, of course, to everyone who joined and listened in today. Please take a moment to fill out the feedback form if you have a moment. And I don't think I have anything else. So thanks again, everyone, for joining, and keep an eye out for our next sessions coming up later this year. So I'll end there.
Thank you. Bye.
Thank you, everyone.
Thanks, everyone.
Thank you.